All right, this is a continuation of thermal chemistry. We're going to be looking at what's called the enthalpy of reaction, either the energy in the form of heat that is either released or absorbed during a chemical reaction. How do we determine that value for the reaction? Well, sometimes they give us what are called thermochemical equations, and in a thermochemical equation, they include the reactants, the products, and then an amount of energy that is either absorbed or that is released through the course of the reaction. And so here, taking something that we're familiar with is the formation of water. Water is hydrogen gas, oxygen gas combining to form water vapor, right? So we're increasing stability here. So as these two more unstable elements combine to form a more stable element, there's an amount of energy that is released to the environment. So what amount of energy is released to the environment? It releases 483.6 kilojoules. Now here, this energy is written as a part of the equation, right? So this, on my product side, I have the formation of water with the production of 483.6 kilojoules of energy. And because that energy is being released, that's an exothermic reaction. So it's releasing energy to its surroundings. Now, sometimes if you're asked to maybe calculate this for a reaction, or sometimes you may see it given to you um, as not a part of the thermochemical equation. If it's just written as negative 483.6, that means that they're telling you that the reaction is an exothermic reaction, that it is given off, it is lost energy. And I think of that, I relate it to like a bank account. If your balance is getting down to zero and then you keep spending and spending and spending and you go past bit zero, then you're going to have a negative balance. So here, this equation is released more energy um, to the environment than it's taken in, so it's got a negative value for that energy. Versus, let's say we reverse this reaction, we're taking a more stable substance, which is water, and we're forcing it to decompose, to break apart. And the most popular way for getting water to break apart is passing electricity through it, right, through electrolysis. So if you pass electricity through water, you're forcing the water molecule to break up, right? And how do you do that? You have to add the energy. The same amount of energy that's required to form the water is the same amount of energy that's required to decompose water, right? To break it apart. So here, changing the water, I'm decomposing the water back into hydrogen and oxygen elements, right? And so whenever you see the amount of energy written as part of the reaction that is on the reactant side, then it's actually taking energy in. So it's going to absorb energy. And as it absorbs energy, that means that it's an endothermic reaction. And sometimes you'll see it written as a positive 483.6 kilojoules. Thinking back to the bank account, right? That I was telling you, if you're putting money in, right, your balance is going above zero, so you're gaining more money, more money, more money right here. So this, how are you gaining that money? You're taking the money into the account. So here, this is a positive value for the 483.6 kilojoules, and that's positive because it's endothermic, right? So those are like your kind of big takeaways from thermochemical reactions. If the energy is written as a part of the reactant, as a part of the reaction, and it's on the product side, that means it's an exothermic reaction, and it's going to be a negative value. If the energy is written as a part of the reaction, and it's on the reactant side, that means it's endothermic, and it's going to be seen as a positive value. So this next question is telling me, well, here we produce 2 moles of water. So what would happen if we produced 4 moles of water? Well, that means that we doubled the amount of moles, went from 2 to 4. So then I would just simply multiply the energy value by 2. I can write the 2 here. It's not letting me do it. Oh my gosh. See if I can erase that and rewrite it. Okay, again, you would multiply this amount of energy by 2 because we doubled the amount of water that was produced. This slide, excuse me, is just more reinforcement from what I already talked about on this document here. So I'm not gonna go over that again. And so here in this slide, it's asking me, what if I was looking at a physical change? Would the states of matter be taken into account, or would they influence the overall amount of energy that's required to change one substance into another? So, for example, here, if I was taking water, my pen's acting up. Okay, so let's say I was converting liquid water into um, water vapor. That's going to require a certain amount of kilojoules of energy to do that. Well, if I added another layer on top of that, let's just say I was going from a solid ice, right? And I want to go to water vapor. Well, first the ice is going to have to transition into liquid water, and then from there I can go back and transition into the gas. So yes, the state of matter that we're starting with is definitely going to have um, an effect on the amount of energy that's required to change from one state to the other. So how is this heat of formation of enthalpy determined? Well, each reaction follows a certain set of steps, right, that we can use to determine the overall amount of energy that was either absorbed or released as heat through the reaction. So what we generally do is we look at the amount of energy that's in the products and the amount of energy that's in the reactants, and we take a difference between the two, right? So here it's the amount of energy absorbed or lost by the system being the reaction, right, at constant pressure. So what is that telling me? It tells me that if I want to find the delta H for a reaction, I take the energy for the products and I subtract that by the energy of the reactants. And if that value is negative, it's going to be an exothermic reaction. It's releasing energy to the environment. If that delta H value is a positive value, then it's going to be an endothermic reaction, meaning that it's taking in energy. So if we go back and we compare this equation here, um, things in nature are going to favor more negative values. Okay. The reason being is that we're releasing that extra energy. That means that our product is going to be much more stable than our reactants were. So things in nature want to become more stable, want to have more stability. So they release that extra energy to increase stability. So most reactions in nature are going to favor they're going to favor these exothermic reactions, these negative values. And that's going to conclude this particular lesson here on thermochemical equations and heat of formation, that enthalpy.